Without further ado, let's move on to the next speakers. Next speaker, I should say, which is Loxley, I hope I say it correctly. Are you there?
Yes, I am there.
Hi, welcome. So you are a senior at the University of Washington. You do a major in informatics, and your focus is on academic developer advocacy. Pretty cool. And you have a talk about quantum computing, which sounds really awesome and a great subscription of that talk. How did you get the idea for this talk?
Well, I first heard about quantum computing 2 years ago when I read Hit Refresh by Satya Nadella, where he said it was literally one of the top 3 things he said was going to change the world, and especially in Azure. And so after that, I've been following learning modules. I've talked to a couple quantum experts, and I've created a very good talk just for beginners to kind of understand the beginning parts of what is quantum computing, how does it work, and how to connect it to Azure. So I'm very excited. This is a topic that I'm super passionate about.
Okay, that sounds awesome. Well, I can't wait for you to start. So I'm not gonna ask any more questions. Really, I love to hear the talk. So the floor is yours.
Awesome. Let's be. Okay. So welcome so much to my Tech Talk. I'm so excited to be here this year. And so we've already gone through a little bit about who I am. And so here I'll just quickly dive into our agenda for this talk. So we'll first cover what quantum computing is and dive into how specifically it works. We'll then discuss why it matters and some really important problems that it has the potential to solve. And finally, we'll tie this all back into how it specifically relates to Azure and how you can learn to implement it right now. And so first things first, what is quantum computing? And to understand the fundamentals of quantum computing, we have to go back to 1935 when Erwin Schrödinger first shared his thought experiment with Albert Einstein. And Schrödinger asked, what if we placed a cat in a box? Or specifically a box with a poisonous substance inside that had an equal chance of releasing or not releasing within an hour. And he said, before we opened the box, we would have no idea whether the cat was alive or dead. It could be alive and dead at the same time. And so the concept of existing in 2 different states at the same time is at the core to understanding quantum mechanics. And this thought experiment was first applied to the concept of quantum computing 50 years afterwards in the 1980s. And so quantum computing is a new computational paradigm. This means that it runs differently than your phone, your laptop, a server, or any other piece of technology you currently own. And what sets quantum computing apart from a classical computer is speed. It has the potential to solve specific problems exponentially faster. And what could take a classical computer billions of years to solve could be solved with a quantum computer in a matter of hours. And so how specifically does quantum computing work? And so let's go back to our Schrödinger's cat example. When we think about a cat being alive and dead, that is fundamentally different from how classical computers work. Right now, our computers run on bits, either ones or zeros that are strung together and sequentially processed. This is known as binary code. Just like how a cat can't really be alive and dead at the same time, a bit can never be a 1 and 0 at the same time. And in addition to being discrete, bits are deterministic. This means that when we repeat the same computation, it will always produce the same output. So for example, if we told a computer to run 5 plus 5, it would always send back 10. And whether you ran it once or a million times, a classical computer would still only return 10. But quantum computing, in comparison, has quantum bits, or that are more commonly known as qubits. And unlike a classical computer that can only be a 0 or a 1, quantum computers can be an infinite or continuous number of possibilities. And unlike a bit, qubits are what's called probabilistic. And so this means that if you told it to add 5 plus 5 together, it wouldn't always return 10. And what makes a quantum computer useful in this way is that if we told it to run 5 plus 5 once, it may return like a different number like 8 or 11. But if we told it to run 5 plus 5 like a million times, it would increasingly get closer to the number 10, which means through repeated computations, like our confidence in the answer increases. And so in addition to that, qubits have two superpowers that bits do not have. And so here we have a visual example of a bit and a qubit. As we can see, a bit can only be a 0 or a 1 at any given time. But let's say you have a single qubit. The qubit can be a 1, a 0, or both at the same time. And when a qubit is both a 1 and a 0, this is known as superposition. Now, let's say you have 2 bits and 2 qubits. A bit can only be one of these orders at any given time, either 0, 0, 0, 1, 1, 0, or 1, 1. But let's compare that to having 2 qubits. When combined, they can simultaneously be all of these values at the same time. And this grows exponentially. For every qubit you add, the number of combinations doubles. And so, for example, if we added an additional qubit to this to bring it to a total of 3, there would be 8 potential outputs. And this superpower is known as entanglement. So what are the benefits of superposition and entanglement? So an exponential number of potential outputs decreases the time it takes for a program to run compared to a classical computer that has to run linearly. And so the following is a really good representation of how a classical computer would solve a maze compared to a quantum computer. So with such a speedier runtime, like why haven't we started learning and implementing quantum computers more in like our day-to-day lives? And there are two main reasons for this that we're going to cover. And so number one is it is debatable on whether we have achieved quantum supremacy. So quantum supremacy can be defined as when a quantum computer can perform a task faster and better than a classical computer. And this is commonly tested by giving the best quantum computer in the world and the same classical computer in the world the same question to solve. And so currently, a classical computer can simulate a quantum computer up to a certain number of qubits. And a quantum computer would need to surpass a classical computer in ability before it could be considered having attained quantum supremacy. And so, but as investment in quantum technology and research improves, this will hopefully soon be achieved. Some sources think that some types of quantum computers can become mainstream in the next 2 to 5 years. And so next up is running a quantum computer is incredibly expensive, or in other words, just very high maintenance. So let me explain. Running a quantum computer can cost over 1,000 times what the same query would cost to run in a classical computer. And this is due to the environment a quantum computer needs to run in. So do you remember in Ant-Man when he had to shrink down into the quantum realm, which was so unstable that he almost didn't make it back out of it alive? And this is kind of how quantum computing works in real life. Like when they are incredibly sensitive to that, so that if any interference affects it at this scale, it'll pretty much disrupt the computer's calculations. And so a couple things are used to control the environment, which is temperature and noise. Quantum computers currently need to run at a temperature of nearly minus 460 degrees Fahrenheit, which also equals about minus 273 degrees Celsius, which, to put that in perspective, outer space is minus 455 degrees. So maybe the solution is moving all of our quantum computers to outer space, which probably won't bring costs down. But so a current challenge, because obviously we're going to be keeping our quantum computers on planet Earth for now, is that we need to run our quantum computers at room temperature. In addition to being insanely cold, it also has to be insanely silent. Researchers are currently creating environments with the lowest noise levels on record just for quantum computers. And so the challenge in controlling these environments makes quantum computers more likely to produce incorrect outputs. So creating quantum computers with error correction or fault tolerance is incredibly important. So in other words, quantum computers are so sensitive that we won't be carrying around quantum smartphones or quantum laptops in the near future. But although these challenges are going to take years and some of the industry's brightest minds to solve, I think it is still possible. And here's why. So classical computers, as we know of them today, have been around for about 70 years and have seen trillions of dollars of investment. In comparison, quantum computers have only been around for about a little more than 20 years. And have seen about $1 billion of investment. And so they've already come an incredibly long way in like the last 20 years. So as investment continues, so will innovation, and they'll soon continue to improve. And so we know about the current shortcomings with quantum computing, it is important to know why quantum computing is still so important and why it matters. And so here are a couple use cases that have the potential to change the world. And so first up is machine learning. So machine learning is based on both sampling and optimization methods, which means quantum computers can help a lot in this space. So quantum computers can provide more distributed and reliable data than classical computers, and can use optimization to show how the machine learning algorithm should be improving over time. Next up is climate change. Quantum computing can discover solutions that would efficiently combat global warming. And this includes creating synthetic fertilizers that reduce consumption of natural gas, as well as make our energy sources, such as disposable batteries, more efficient. And finally, there could be major breakthroughs in healthcare. Classical computers can take years to process the complexity and accuracy needed to create medical treatments. But a breakthrough in quantum computing would mean treatments could be optimized and developed exponentially faster. So as we have covered, quantum supremacy could be possible, like quite literally within the next 10 years. So, and the great thing is, and like to get prepared for that, the best thing we can be doing right now is learning it and experimenting with it so that we're prepared for when it starts transforming these industries. And the great thing is Microsoft is aware of how important quantum will be and is baking it into the Azure ecosystem right now. Today, you can run a quantum solution using a simulation on a classical computer, and even with a real deal with Azure Quantum. And finally, even cooler, Microsoft has created the open source quantum development kit known as the QDK, which includes free libraries as well as the programming language Q#. And so I highly recommend to learn more to check out Microsoft Learn's Quantum Computing Foundations module to learn more of how to create your first Q# program. And so if you try out quantum computing, I would absolutely love to see it. Tag me on Twitter with what you create. And thank you so much for coming to my talk. I hope you learned something new about the awesome world of Azure today. Thank you.
Yes, that was a great explanation, actually. That was really awesome. And
Awesome.
I looked at the chat and people were asking questions and then you were answering them already.
That's awesome. Wow. I don't know if there's any questions I didn't answer we have time to cover.
Let me just see. Something came on. Someone that says, as a developer, I'm worried about quantum computing since it can decrypt RSA keys very fast with the formula. So what do you think? Would it also be something that could be used for evil quantum computing?
Oh my gosh, that's actually something that I've done like a little bit of research in. And there's kind of this discussion that it's like, if we created quantum computers, we would be able to pretty much like break any password that currently exists in like a matter of seconds, which a classical computer would take like, yeah, just like millions, if not billions of years to crack. But I've heard that kind of like the alter side to that is if we're creating like these quantum computers that can kind of crack these passwords, we'll be creating quantum solutions that can also like make our environments more secure. So in the one hand, it does have the potential for evil, but on the other hand, we're investing in the technology right now so that when people start to use this tech for bad, they'll be like, yeah, superheroes there to like save the day. So I think as of right now, I'm confident, but it would be interesting to see what the next decade brings. I'd be super interested to hear about that.
Yeah. Well, it's really interesting stuff. I have one last question, a personal question I want to ask. I looked at your blog and I saw you were working on the Seasons of Serverless challenge. How do you find the second challenge? Have you done it already?
That is what I'm doing right after this talk, actually. But I actually was writing an article about custom vision like 2 weeks ago. So I'm like literally super prepared to go in and start working on it. I'm actually so excited about working on it. My goal is to have it done by this Friday, and I'll probably make an announcement like this weekend once I finish it.
Oh, really cool. Well, we're going to read that. So great talk. Awesome. And I really learned something. So thank you so much.
Awesome. Thank you. Have a great rest of your day.
Thank you. Same to you.